Hello, college algebra enthusiasts. So, all right, so let's take a look at how do we use logarithms to model some natural phenomena, and then how do we use these models to solve some of these problems. So we are dealing with coronavirus, so probably it's the right time to talk about some sort of a modeling of a spread of a disease or a spread of a flu. So that basically is modeled using logistic growth, right? One of the simple model of any spread of a disease is using a logistic growth model, what we call logistic growth model, which is something like this, where f of t, or the amount of people who get infected, is basically c is the basically your amount of population, right? Amount of population divided by 1 plus a. A is some sort of a constant. E to the negative b is also some sort of a growth constant, you can say, for the virus to grow, and then t is the time. All right, so that is the model that we have, and that's what we are going to use right here. Let's take a look at this. So a couple of things in here. Usually, the model, right? If you try to look at the growth model, they have this kind of a nature. So initially, it starts at some value, it keep on increases. The growth rate is high, 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 and then the growth rate becomes small. Growth rate becomes smaller. So it kind of like now growth is not as fast as before. It kind of grows like that. So whether it doesn't matter what kind of population is, even if you take a look at the our coronavirus has a very similar thing. So for example, let's take a look at the coronavirus. So here's the data as for today, right? So here's the data that we have as of today, as we speak right now. So if you see here in any model, so this is for the you see here this the kind of growth is kind of if you look at the US, you see that the growth is kind of keep on going. That's the kind of a growth, right? We haven't reached this particular point yet. We are still somewhere over here. So which means we still have maybe, I don't know how long, hopefully it's sooner, but we don't know how long it's going to take, right? So that's where we are. So the kind of grows like this, right? It kind of grows like this. So if you take a look at the daily increase, you see that it kind of grows like that, and then eventually once after is reaching its peak, then it's going to, usually it's symmetric, not completely symmetric. Sometimes it's skew symmetric, but eventually will go. So for example, if you take a look at the South Korea, right? At least the data that is reported, you see that the population, the increase, right? The daily increases, kind of like it reached the peak and then it kind of came down and kind of like slowly becoming a zero. And if you look at the graph, you see that the graph is, kind of like going along. Now it reached the peak and then it's kind of like, still going. It did not become kind of like a steady. It kind of still reaching, but it's a very slowly there. So that's a kind of the usual growth. And you see here logarithmic, right? For those who can see. So this is kind of, modeled using logarithmic function. Even if you model it, you see that, it has this kind of a graph right there. If you take a look at the China, let's see how things are in China. So you see that, even in China, they are saying, it reached the peak, now it's pretty much slowed down and things like that. Let's take a look at the daily increase, right? So here is so there is some sort of an anomaly here, maybe in terms of something is not, there's some sort of an anomaly in there. I don't know what's going on there in this particular region. If you take a look at the daily increase there, right? So usually, it kind of goes like this. It reaches the peak and then comes down here. And again, I think, these are unusual. These kind of usually it's a symmetric. These kind of daily increase is unusual. But again, we don't know how things are. So we will take as per the reported ones. All right, so here's that's how the growths are. The growth has usually something like this, something like that, something like this, and UK is still going up, Turkey is still going up, Switzerland kind of like a coming down, Belgium is going up, and things like that. Now South Korea seems to have come down, and so on. So that's how these these models are. That's how it grows. So the one thing that we can say by analyzing this model, again, this is a very simple model, by analyzing this, what we can see is when t goes to infinity, ladies and gentlemen, e to the negative bt, since b is a positive, b is a positive kind of like a growth rate, we can figure out with the data. We'll talk about it later. When t goes to infinity, so you're going to have e to the negative infinity. And e to the negative infinity is actually is 0. So therefore, what you're going to have is, as t tends to infinity, as the time approaches longer and longer, eventually this is going to become c over 1, which is equal to c. In other words, after infinite time, theoretically speaking, everybody will get infected, right? So one of the reasons that, why they say, it's not like you cannot control it, since we are all interconnected. One of the reasons that we are saying flattening the curve. You heard the term flattening the curve, right? So basically, we try to control the spread rather than going like this. Then we may not have the capacity of our medical system might not be able to handle that. It might be short-lived, but it might go up and then come down eventually. Or the better one would be, kind of a spread slowly and then reaches this and come down. So eventually it'll reach everybody. But the thing is, hopefully by doing this, our medical capacity, we can keep it under the medical capacity. So that's what they are saying, practice social distancing, avoid, use some precautionary measures, washing the hand and things like that. So that is the idea of, this this flattening the curve. This is that flattening the curve idea there. So eventually it'll go to everybody, unless if you stay inside, if you're sheltered at home, if you're isolate yourself in a way, then the impact is going to be after a couple of weeks. If everyone around you gets infected, and then and after they get infected and they become recovered, then hopefully, if you don't have exposed to anybody else, you might not be able to get it. But again, the chance of not getting it is really, really low. But if you have any underlying conditions, you must really stay away and not get it. Anyway, that's a general idea of these spread of the flu. So let's take a look at the modeling that we have. The very simple model, again, as I said, we have here is f of t equals to 30,000 30,000 over 1 plus 20 e to the negative 1.5 t, and that describes that particular model there. So although what I did not tell you in this particular model is the following, is that there's only 30,000 inhabitants. See, the maximum people that can be infected is going to be 30,000, and that's what we have, the carrying capacity of that virus, right? The carrying capacity, or the maximum that it can reach, is going to be 30,000 people, because there's only 30,000 people in there, right? So the question here is a couple of things. So after the data that we have, we can look at, so somebody modeled this. So the question here is, how many people became ill with the flu when the epidemic began? Question number 2 is, how many people were ill by the end of 4th week? And the third question is, what is the limiting size of the f of t, namely the spread or the amount of population that will become ill? So now we have data. Probably I'll give you a problem at the end. Using this data, you can actually predict, see what happened, how for the past 3 weeks or 4 weeks, you can actually predict how many, if the current rate continues, you can actually predict, you can try to fit the problem, our coronavirus model into this, and predict what's going to happen in 30 or 3 weeks from now or 6 weeks from now, and things like that. Actually, you can predict it. Anyway, I'll talk about this problem later. Let's try to solve this problem. So how many people became ill with the flu when the epidemic began? So which means we are looking at initial population. So therefore, we are looking at f of 0, right? The time is equal to 0. And when I plug in 0 into this equation right here, so I'm going to plug in a 0 here, which means I'm going to plug in a 0 over there. That is going to give me 30,000 divided by 1 plus 20 times e to the negative 1.5 t, right? And that is going to be, this t is going to be replaced by 0, right? This t is going to be replaced by 0. When we do that, then this is going to become 30,000 over 1 plus 20, which is 30,000 over 21, And if you simplify that, that is approximately 1,429. So the initial amount of population, those who got infected, is for 1,429 people. Let's take a look at the part B. Part B is what happens after 4 weeks, right? So which means we are looking at f of 4, which is, again, by the formula, it's 30,000, and the whole thing is divided by 1 plus 20 times e to the negative 1.5, and t is equal to 4, which is 30,000 over 1 plus 20 times e to the negative, that's 0.6, right? That's e to the negative 6. So when you do that, what's going to get us? You're going to get approximately, that is going to be 28,583. So that's basically pretty much everybody, right? After 4 weeks, pretty much everybody got infected with that particular model. Let's take a look at the part C. The part C is what is the limiting size. Limiting size is basically the number of people in the town, and the number of people in the town is 30,000. So if you take a look at this equation, the equation is f of t, which is going to be 30,000 over 1 plus 20 e to the negative 1.5t. As I've said earlier, when this t goes to infinity, this whole thing is going to be infinity, and e to negative infinity is 0. 20 times 0 is 0, so all I'm going to have 1. So this eventually is going to become, as t going to infinity, this is going to be 30,000 over 1 plus 20 times e to the negative infinity, which is 30,000 over 1 plus 20 times 0, which is 30,000 over 1 plus 0, which is 30,000. So the limiting size in this case would be 30,000. And that's how we solve this particular problem. So for those who are interested in coronavirus and to do some research, right, interested to do something, you can model that. So for example, go back to a couple of weeks data and try to fit this. So the formula is f of t equals, the US population, let's just say 300 million. So that's right, and the whole thing is divided by, I'm going to say, if you take a look at the population, right, this is going to be, as you see here, 1 plus a e to the negative bt. So it's going to be 1 plus a e to the negative bt. So what you can do, you can take a look at 2 weeks ago. We don't know again when it was. 2 weeks ago, look at the data. Whatever, let's call that as the initial one, right? Let's call that as the f of 0. And or f of 1, let's just say, or 2 weeks ago, let's call that as f of 2, right? Maybe that's the second week after the spread, right? If you want to, so let's just take that. And then, I don't know, whatever the number of infected people, write that down and set that equal to 3 million over 1 plus a e to the negative bt. So you're going to have an equation, and then solve that equation. You're going to have some sort of an equation there. Try to find the f of this week, right? You know the number of population who got infected, and then you say that is 3 million. Sorry, 300. I shouldn't say 3 million. So 300 million, right? 300 million, and this is also 300 million divided by 1 plus a e to the negative b. So it's after 4 weeks, right? We're calling it as after 4 weeks. So let's call that as after 2 weeks. And then now you're going to have another equation, right? So we have 2 equations and 2 unknowns. Using this, try to figure out the a and b and see what you get. See what kind of equations that you get. Using that, you can kind of model, our coronavirus using that way. And then using that, you can predict what's going to happen, 2 weeks from now, or 4 weeks from now, and 5 weeks from now. Again, this is a simple model. This may not represent the reality, but this can give you kind of a good understanding, the basic understanding of, how things are in general, right? Again, this is not going to accurately portray the numbers, but this can be very helpful in getting a very crude estimate of how things are going to go in the next few weeks. If you have any questions on this, again, I'll be happy to answer them during my class. I will stop it right here. I will see you all later in chapter 5. Have a great day and have a great week.